Seems everyone's staying home today.
It's always on Friday.
Huh?
It's always on Friday. So
Alrighty, so here we are again, and we're slowly, but actually this chapter is going to go pretty quickly despite kind of how dense it might seem. But we are making our way through the kinetics chapter here. And last time we had introduced the idea of kinetics and kind of talked about the difference between an instantaneous rate versus the average rate, and just kind of set up the basics for expressing what kinetics is. One of the challenges that I remember, at least when I went through this chapter as an undergraduate, was just kind of wrapping my head around it all. It seems very complex, and it is, and it can be, and it might seem that way, but really at the end of the day, we're just figuring out a way how to calculate how things change with time is all it is, right? And so today we'll bring in a little bit of calculus and talk about integrated rate laws and all that kind of stuff, but it's not going to be maybe as intimidating as you guys might expect, right? We'll break it down about as simply as we can get. And we'll look at a couple of example problems, and then as we tend to do at the end of the chapter, we'll probably spend a day or so kind of just working through some different problems and things like that. Right? I'll have a quiz up for you guys again for Friday, not on kinetics, right, but on the previous chapter there, right, with the colligative properties and that kind of thing, right? So keep an eye out on that. I still have to grade your other one there. It's just, Mondays and Tuesdays going to be busy days for me, so I haven't gotten to it yet. Don't worry, I'll get to it. We'll get it all knocked out here. I think that's kind of all I needed to. Oh, so not next week, right, but the week after, right, is the first exam for you guys, right? So I think, what is it, the 8th, the week of the 8th, I believe is what it is, 9th. So whenever you guys have lab, right, we'll be doing or whenever you guys have the off day from lab, there is when we'll be doing the exams, right? So just something to keep in mind, right? So as you guys are starting to prepare and put things down in your calendar. But I think that's kind of all I wanted to mention. I can't think of anything else. So, and we'll get started with prayer, and then we'll continue on here then. But Lord, we just thank you once again that we can turn our attention to you whenever we want, Lord. And we know that you're listening to us, and you'd like to hear us, and that you'd like to spend that time with us also, Lord. So we just thank you that we have that opportunity just to speak with you whenever we want, Lord. And we pray that we just use those opportunities more each day, and that we can use that time just to draw closer to you, Lord. In whatever way that might be, in whatever way that we might need, Lord, we pray that we can just take that extra step towards you today. We just ask that in your name. Amen. All right. So, where we had ended up, we had kind of introduced the basic rate equation, right? So the rate of a reaction is equal to some constant times the concentration of the reactants, right? And so that's kind of our basic equation there for the rates, and that's kind of how we're going to set everything else up, right? So when in doubt, here's your standard rate equation. Now this is going to change a little bit here and there, and we'll talk about some of these variations today, but that's kind of all it really comes down to, right? So, let's see what else we can learn about this. So a general equation, or a general reaction, we'll use the rate law, that's what I was just trying to say. There's a breakdown of what K is, and then we'll see these exponents. So we'll spend a little bit of time today just calculating or figuring out how to look at, or how to calculate those exponents, M and N up there. But when the book refers to it, when I call it out, or when I'm talking about it, right, M and N are the order of a reaction. The order of a reagent, and then the overall order is the sum of M plus N, and that's for the reaction itself, okay? So later on today, we'll talk about zeroth order and first order and second order reactions, and that's what we're referring to there, okay?
What's the in B?
Just whatever, generic, reactions. Typically, we'll see these orders as integers. Most of the time, they're going to be positive. In fact, I really can't think of a time where I've ever seen an order come out to be a negative, but I'm sure there's, there's probably an example or so in the book there somewhere about it. But, and the same thing with fractions. Sometimes they could be fractions, but again, it's not really something that I recall seeing all that often. I know it's not in my slides, I don't have an example of that. But just something to pay attention to, right? There's no real limits, I guess, is what it's saying with the order there. Could be negative, could be fractions, could be whole integers. For the most part, we'll be dealing with nice integer values for this class, though, is what it is, right? Especially when we deal with some of the more advanced topics that we'll deal here with. Okay? So there you go. Cool. So how in the world do we determine these rate laws and figure them out and all this kind of stuff, right? So that's the question. Now that we know everything there is to know about writing the rate expression, right? How do we actually start to figure them out and put them together, right? So up there, they cannot be predicted from reaction stoichiometry. And what I mean with that is we can't directly take the order from the stoichiometry itself. Now that's going to be a little bit more relevant later when we talk about equilibrium, where we do have to take into account the stoichiometry, okay? So right now you're just like, okay, reaction stoichiometry doesn't tell me the order, but later as we start to add some more information this semester, then that might start to overlap in terms of ideas or confusion or whatever you want to say there, so just keep that in mind, okay? So to find the order for a reactant, we run the experiment with a known set. So later on, again, we'll come back to this and I'll point it out again. But whenever you see that subscript 0 there, we're just talking about an initial concentration, okay? So you could even substitute out that 0 for I if you want to, right? So some type of initial concentration, right? And then we measure the initial rate, right? That's going to be based off of the slope. We'll talk about that also. We keep one thing constant and we change something else and we remeasure and we just set up a series of experiments where we change one concentration, right? And we keep one thing constant. Then we set up another reaction where we change the other thing and keep the first thing constant. And we just stack a series of reactions with data for this, okay? So it's a very typical set of reactions and conditions and questions that come out of this chapter is for you guys to calculate the order of the rate law, right? And even to figure out what the rate constant is, right? But this is the basic idea. Find one thing that's held constant, find the one thing that changes, and compare it to another reaction that gives us the data that we need, right? So something like this, okay? So if we have this generic reaction here, right? We set up an experiment where we just, we choose some kind of arbitrary concentration. It doesn't really matter, right? You just have to start somewhere is all it is. And we can measure the rate from that, right? We hold one thing constant and we change the other one. Now, if you take a look at it, once you set the initial rate, once you set the initial concentrations, it's not arbitrary at that point how you change the concentration, right? So if you notice, we double the concentration here, right? So that is one thing to start to pay attention to. Where and how do we increase the concentration for the things that we are varying, okay? Then we set up a third experiment where we keep this constant and then double the other concentration there, and we remeasure the rate, right? And you'll notice in each case the rate changes, right? So when you're approaching a problem like this, the first thing you guys need to do, right, is write out your generic rate expression here, right? Because the job that we're going to have is to solve for what m and n are, okay? So if you see a problem like this, start out by writing your rate expression, right? The rate is equal to the constant times the concentration of A, right, to some power, times the concentration of B, right, to some power there, okay? And then we're going to start to plug in the numbers to figure out what the m and the n are. Make sense? It's going to be really tricky math. You have to divide things. Right. So let's take a look at this, right? Let's do a little visual inspection, right? So if I take a look at experiments 1 and 2 there, right, I double the concentration of hydroxide, and what happens to my rate? It doubles also, right? So what does that tell you? If I double a concentration, I double my rate. What's the relationship between concentration and rate then?
Proportional.
Yeah, right, they're directly proportional, right? If I double one thing, it doubles the other, right? Got it? Let me compare experiments 2 and 3. Now we hold the hydroxide constant and we double the ester here, right? And again, we see the same thing. As we double the ester, we double the rate. So what does it tell you about the concentration of the ester there? It's proportional also, right? Directly proportional. Do you guys get what I mean with that? If I multiply one thing by 2, I multiply the other thing by 2. You catch what I'm saying with this, right? That's the math that we're going to figure out. But we have to put that into context of exponents is what it is. Right? So for what exponent can I hold a ratio constant there? Right? If I double something, it doubles my answer, right? That kind of thing. Okay? So that's why the rate expression here is looking like that. What are m and n? Well, they're both 1 in this case. You guys catch what I'm saying with this?
No.
Okay. So let's see if we can take this idea then. I think I got space here, right? And let's put this into a mathematical expression. I can't find my pen. There it's going. So just I'm gonna kind of follow along with what I was doing here, right? Oh, everything changed around on me. That's weird. I have to figure that out. Anyway, different for a different day, right? Okay, so what we're going to do is compare experiment 1 to experiment 2, right? So what is the rate equation for experiment 2? Okay? So it's going to be equal to 4.5, right? Well, let me back up here for just a second before we just kind of launch into it, right? The rate expression for experiment 2 is going to be equal to the rate, okay, this, times K, right? Times a concentration of, we'll just call this, I don't feel like writing all that out all the time. All right, so I'll just call this A right here, okay? You guys following along? I don't feel like writing all that stuff all the time. It's some constant, right? Times OH to the N. Got it? That's the rate expression for experiment 2. Can we fill in values for those different parts of that equation? Do we know what the rate is? Yeah, it's 4.5, right? Do we know what K is? No, not yet, right? We'll get there. Do we know what the concentration of A is? Yes. Do we know what the concentration of hydroxide is? Yes. So what are we missing? We're missing K, we're missing M, and we're missing N. Got it? So we need to set up an equation to kind of eliminate some of that stuff for us so we can start to figure out some of these variables. Okay? So let's plug that in together here, right? So if we take this and put numbers, 4.5 times 10 to the negative 4 is equal to K times 0.04 to the M, and 0.08, right, to the N. Oh, I'm sorry, I'm being dumb here. I apologize, guys. I wonder. Okay, sorry about that. Okay. So what we need to do is compare this to the rate, right, of where we hold this stuff constant. Or hold one of these things constant. So what's the rate expression for experiment 1? What's going to be equal to rate? Right? Rate equals K times the concentration of A to the M, right? Times the concentration of hydroxide to the N. And again, we have the values for all those different components, right? So here's what I mean. 2.2 times 10 to the minus 4 equal, right? K times 0.04 to the M, 0.04 to the N. You guys with me on this one? Do you guys see what's starting to happen here then with the math? So So if I just put one over the other, right, if I compare the two, let's take a look and see how this math simplifies here then, right? So let me take this, duplicate. So if I divide these two rates, right? What is K? It's a constant, got it? So if I divide K by K, what does it turn into?
Nothing.
1, right? We don't know what the value of K is, but we do know that if we divide K by K, it's equal to 1, right? So we can essentially cancel that out. Got it? Do we know what M is? No, but we have 0.04 to the M divided by 0.04 to the M.
I thought you said we did know what the M was.
We don't know yet, we're figuring it out, right? I mean, we could look at it, you know, in visually, but I'm saying how could we calculate it, right? That's what we're doing here. So if I divide these two, what does this turn into? 1, right? You guys with me? Right? Now, we can divide 4.5 times 10 to the 4 divided by 2.2 times 10 to the 4, and it's equal to about 2.05, right? If I divide 0.08 to the n divided by 0.04 to the n, what is it equal to?
0.02?
Not 0.02, just 2, right? To the n. So what does n have to be equal to for this to be true? 1.000000 something, right?
Some loggy thing.
1 time, 1.000 with a bunch of stuff and then a couple other numbers, which in practical reasons is what? 1. Got it? Do you guys catch this math here? That's not too bad, right? Do you guys see what we're doing? We set up the two equations to cancel out the stuff that we don't know, so we can simplify to an expression of one of our variables that we can actually calculate. Got it? That's all it is. Good? Yep.
So what's the value of M in that one?
Good question, right? We don't know, right? We couldn't set up the equation in a way to figure that out directly. But that takes me to my next question. Now we know what n is, right? So now we need to set up the same type of ratio, right? The same type of dividing, right? To figure out what m is. Got it? So now what do we need to do? To figure out m, right, we will compare 2 and 3. Got it? So see if you guys can get that set up. Set up the ratio there, the dividing, right? The comparing the two rate expressions for experiments 2 and 3.
Would the expression with like the higher value go on the top?
It wouldn't make a difference, but that's typically what I do.
Okay.
Because if you flip this, right, you'd have 1/2 is equal to 1/2 to the n, right? So
Okay.
maybe it would make it maybe a little bit harder kind of visually to look at, right? But the math would come out the same.
Alright.
So what we want, right, is the rate of 3 over the rate of 2. So set up your expression for that. otherwise you'd be right, you got the right idea. One. Oh, cool. Good. Yep. There you go, fantastic. Good looking. Good, so, I think you copied the number incorrectly, so from 3 to 2. And these would be, this one up here would be 0.
Oh.
Yeah, otherwise you're like, hey, wait a minute, L equals 0. Or an L equals 1, I mean, yeah, but. Awesome, all right. So we'll start to fill stuff in, right, so, 9.0 times 10 to the -4 is equal to K, 0.08 to the M, 0.08 to the N, 4.5 times 10 to the -4, and 0.04 M, 0.08 to the N. Good, right? A cancels out with K, 0.08 to the N, 0.08 to the N, right? 9 divided by 4.5 is equal to 2. 0.08 divided by 0.04 is 2 to the M, so M is equal to 1. Got it? Some of you guys had it flipped, and that's just fine, right? You still get to the same answer, right? What's up?
Would you not plug N into it?
You could if you wanted to, right?
I mean, I know it doesn't really make a difference here, but if the other numbers were different.
So if you have a case where you have completely different variables, then yeah, you'd have to find one of them first, and then you could plug it in. Cool, so what does this all tell us? Right, remember the question, or what the question is going to ask is, what is the rate expression for this equation, right? So overall, then we would say the rate is equal to, right, K times the concentration of A, right, to the 1, times the concentration of hydroxide to the 1, right? Now obviously, do we need to put those 1s into our expression? No, right? But just for emphasis sake, right, these are the ones that we calculated there. Okay? So the individual orders, hang on just a second, right? So the individual orders are 1, and the overall order is 2, right? 1 plus 1. So I don't know who raised their hand first. So.
Why'd you put A there?
I don't feel like writing out the whole. Yeah. Right, so I just said this is equal to A, right? So you guys can plug that in. Right? It's me being lazy. I mean, not lazy, we call it time efficient, right? There we go. Calorically efficient, time efficient, whatever you want to say. Yeah.
So what does that actually mean? What do the 1 and the 1 and the 2 tell us?
It means there's a direct relationship between the increase in concentration of one of these and how it affects the rate, right? If I double one of those, then the rate gets doubled, that kind of idea, right?
Okay.
Good question. Cool. So now we're just kind of missing one little part. Once we've got our orders figured out, right, our exponents there, then the question typically asks, what is the constant, right? What is the rate constant for this reaction? Well, now we can kind of easily plug that in together, and I gave you guys some space there. Right? Once we know the rate law, we can calculate K, because we know what the rate is, right? So we have the data from that chart, and we can just plug in the two concentrations, and we can back out what our value of K could be, right? And that is the rate for that particular, excuse me, that's a constant for that particular line, right? Good? That's not too bad, right? The tricky part of these types of questions is making sure you copy the right values for your concentration down when you're setting up your fractions, right? Just make sure, double check, always double check, go back. Typically, you will see these fall out to be nice integer values, right? But always go back and double check your math on these, make sure you copied it down. Okay. Cool. And like I said, we'll come back at the end of this, at the end of the lecture for this chapter, and we'll do more of these types of problems. Okay, so now, as I promised, we'll get into stuff that seems like, I remember when I went through this, I'm like, why, what's the point? You know, why must we pile on the misery? But there is a rhyme and a reason, okay? So if we integrate the rate law, we get to a new expression, right? Now, I'm gonna skip all the yada, 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 it's in the book, you can look it up online if you wanna know how we get there, all these kind of things. It's not important to me, right? I'm not here to teach you guys math, right? We're here to apply math, right, to a chemistry setting is what it is. So we get a first order integrated rate law is what we end up with here, okay? So what does this tell us? Now here, the natural log of a concentration of A sub T and the natural log of the concentration of A sub 0, these are the two parts that, I don't know, I always had trouble kind of rationalizing. This is my initial concentration. Remember I said that if you see that A sub 0, right, that's just our initial concentration that we're looking at, okay? A sub T is the concentration at a given time, which is this value of time here. Got it? So if I give you guys an initial concentration and I say, what is the concentration after 500 seconds, right? If I give you an initial concentration, I say, what is the concentration after 500 seconds? You plug in your T and your K, and you can figure out what our concentration is using this equation. Got it? That's all it is. That's not too scary, right? Just here's a concentration, let the reaction run for some given amount of time, and then we can back out the concentration after that time is done. Good? All right. Now we've got three integrated rate laws, a zero order, a first order, and a second order. They all are worked the exact same way, right? They look different, right? But you see again, we have an expression of our initial concentration, a given time, and then our concentration after that time has passed. Yep.
I take it we'll need to memorize those?
No. There's no need to memorize those. I will always give you guys those equations. Okay. I don't even have them memorized. I always look it up. Yeah.
So do we choose one of those three based off of the order we
Yeah.
calculated?
Right. That's what we'd have to assess it, right? Given the order of your reaction, right? Those are the types, or we have to pick which one to use, right? Now, on the other end of things, yeah, what's up?
How do you know the order of the reaction?
How do we know the order of the reaction? What is the order of a reaction?
M plus N?
Right? Those are our exponents there, right? So for the example we just worked through there, right? The M and the N, right? That's what we would use to assess the order of a reaction. Okay? Cool. So to kind of build off your question there, Andy, right? So when we're in the lab, right, and we're starting to figure out what order our reaction is, right? We would go through and we could do all the data that we had there and all these kind of things, and we'd come back and we would put in the different values here and plot them. And what we would find is that when we find a linear plot, that corresponds to the order of our reaction also, right? So I think there's an experiment that you guys do where you kind of back this out. I know we used to do it. I know Dr. Tong has been kind of putting in some different labs and stuff, right? But we just measure concentrations. You guys, plot it in three different ways, right? The concentration versus time, the natural log versus time, the inverse concentration over time, and you figure out which one's linear, right? And that gives you a quick way of figuring it out also. Good? You guys scared?
Oh, absolutely.
It's not too bad, right? It's always one of these things where I love watching the videos for the integrated rate laws online because they, they always go through these really lofty explanations about what it is. And I'm not dismissing that. I'm not saying it's not important or relevant or doesn't come into play, but I'm just, what's the point, right? Is kind of what I get to, right? Is the point to sit here and, slam in what calculus is and what a differential equation is and all that kind of stuff? And the answer is no, right? My opinion is always, this is our way of relating initial versus concentration after an elapsed point of time. That's all it is. We just have to make sure we pick the right equation, right? That's all.
Is it in calc or is it trig?
No, it's calc, right? When we're talking about integration, that kind of stuff.
Okay.
Yeah.
I just want to clarify, you just said that as a way of relating, concentration over,
Some elapsed amount of time, yeah.
that is what an order reflects?
No. That's where we apply these equations,
Okay.
right? That's where we apply these equations.
Okay.
And order just refers to the relationship between the concentrations and the rate,
Okay.
right?
And then, sorry, excuse me, is the order the overall?
Yes.
Okay.
Yeah. Yep.
Okay. Where are we integrating?
Mm-hmm.
Where are we integrating?
So remember, when you're integrating, you're looking at changes in time is what it is, right?
Mm-hmm. Okay.
Okay,
Sorry, I'm just like,
That's okay.
I'm used to integration coming with the evil squiggle line.
it's there, it's just we skip all that part.
There.
It's in your book if you wanna go through and look at it, right? And like I said, it's not a hard integration, it's just, I don't see the point in doing it here.
I did enough integration studying for my calc quiz today.
There you go. Cool. So just a maybe example of how we would see this presented if we were doing this in the lab, right? So if we measure different data, right, for this particular reaction here, where, what does it look like we're doing? The dehydrogenation of something, pentane, right? Whatever it is, I don't really know. So if we're doing that reaction up there, right, we would plot out the different values that we have for concentration and time, and we would just say which one of these is linear, and then we would know what the order of the reaction is, right? Alternatively, we could go through and do the assessments that we did on the previous example where we set up a bunch of different equations and figure out which one it is, right? Based off of that. But either way, right, this is the way that we would practically do it when we're discovering or when we're making up a new reaction in the lab.
What's zero? What is zero?
Zeroth.
Zeroth?
Mm-hmm.
That's a word.
Sure.
Okay.
You can prove me wrong.
I have to.
So the application for this, at least the way that we present it for this class, is the idea of a half-life. Now, just for, I don't know, maybe historical sake or something, one of the topics that we used to cover in the second semester of Gen Chem is nuclear chemistry. And we used to talk quite a bit about, alpha particles and beta particles, and nuclear decay, and fission and fusion, and these kind of things,
When
right?
do we get to talk about that anymore?
Why?
Yeah.
The answer to that is because, so the curriculum is kind of set by a national committee. And they said, we don't need this anymore in Gen Chem, right? So now what's the word I'm looking for here? The cultural reason why is different, right? But that's a great question, and it's an important question.
Is it because they don't want us knowing how to make nuclear bombs?
No, it's just because of culturally everyone's scared of nuclear energy, right? Because it's gonna explode and we never know when, right, that kind of thing. So there's really, the job market for nuclear engineering, that kind of stuff is very, very, very limited in the United States, right? And so we just don't run into that many students, and so they're like, okay, we don't need to teach it anymore, right? Although from the nursing side of things, right, nuclear chemistry is actually extremely important, right? So I'm always of a different opinion on what they do, but hey, right, I'm just here to teach what they, within the context that I'm given, right? Anyway, so half-life. So what does it mean practically for us, right? So at the top there is maybe the statement that we'll keep pointing back to, right? The time for an initial concentration to reach half, okay? So half of your stuff reacts, right, changes into something else. That's all it comes down to, okay?
So we're considering half-life not as just the decay that stuff goes through naturally, but specifically the speed of the reaction?
Yeah, you could think of it like that.
Okay.
right? Now, and this is important here because that's gonna simplify our math for us. Half-life are only useful for first order reactions, right? Because, right, then the time is dependent on the starting concentration, right? And this is a constant for first order. If you don't have a first order reaction, we don't have that same statement doesn't hold true. And so we can't approach it in the same manner. I'm not saying we can't figure out what the concentration is after a given amount of time, right? We have those integrated rate laws, but what I'm saying is when we're specifically dealing with half-life, where the time drops exactly to half the concentration with a first order reaction, then we can apply what we're about to do. You guys catch what I'm saying with this? We can always calculate the concentration after a given amount of time using the equations that we just looked at, right? But specifically with first order, we can have kind of this special case fallout that we discussed with half-life, okay? That's all it is. All right, so let's look at some quick derivation here, I think. Okay, so what's going on, right? So take a look at the top, right? We start with the integrated first order rate law, right? The natural log of a concentration after a time is equal to the negative constant times T plus the natural log of the initial, right? If I'm dealing with half-life, then my, right, concentration is equal to half of the initial, right? That should have a sub T there, I guess, if we, I guess I left that out. So let me put this in here, right? There it is, okay? After a given amount of time, half of it, right, it's going to be equal to half of the initial concentration, okay? So I can take that, put it into my natural log, right? Simplify some things together using some math, right? Using natural log math there, which I always forget. I always have to remind myself every time I go through this chapter. I just don't deal with natural logs all that often, right? This will simplify into the natural log of 1/2, right? Which is equal to the negative of negative natural log of 2, negative times k times t 1/2, which blah, 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 simplifies into this right here, okay? So, the time, the half-life time, right? T 1/2, the time for something to get to half of its concentration is equal to the natural log of 2 over the rate constant. That's all it comes down to. Does this make sense? Well, it should, right? Because remember, the definition of a half-life is we were saying it's going exactly to half of it, right? So essentially that simplifies the concentrations down to a constant, if you want to think about it for that, right? That's where that natural log of 2 kind of comes from there, right? It deals with the concentrations. So T 1/2 is equal to natural log of 2 over K, or sometimes in the book you'll see it like 0.69 something, something, something. It's the exact same thing. I don't care which one you guys use, okay? Good? So what does this tell us? Right, for a half-life, now we can figure out the rate constant if we know the time that it takes to get there. Or if we know the time it takes to get there, we can figure out the rate constant. Right? We just have an expression that relates time and a rate constant there is all it is. Not too bad either, right? Maybe a little bit confusing, but that's okay. Give you guys a second to copy that down, and I think we'll have a practice problem, a couple practice problems here coming up.
Okay, so do we need to know this whole process or just
Nope.
the final thing?
Yeah, this is just to prove that I'm not, pulling stuff out of
Okay.
nowhere. Okay. Alright. So visually, how does this look? We have cisplatin, a chemotherapy agent. We can graph out the concentrations over time, right? And we can see exactly where it halves the concentration, and so we can get a numerical value for its half-life there, right? So we can figure out the rate constant, right? If we plug in the time, divide it, the time divided by the constant there, we can map that out, right? That's all it is.
How come it's curved?
It's not a linear relationship, right? That's all it's saying. All right. So let's think here a little bit. We have a first order reaction, and we give an initial concentration there, and we give the half-life, right, T 1/2 of 400 seconds. So there's 3 different things that we need to figure out, okay? Maybe in a second I'll start copying stuff down and then I'll give you a push in the right direction. So, what's important to recognize from the given information here? Okay, well, I think I don't have to point out that, under knowing the additional concentration is important, right? I think you guys got that. And we give you a time. What is important to recognize, though? That this is a first order reaction. Because do you get what this question's asking you in part A? What is this question asking in part A? What is the concentration after a given amount of time? Right? What's the concentration after a given amount of time? So what equation do you guys need to do that? What's our equation that can relate concentration after a given amount of time? Our integrated rate laws. Got it? Now we have 3 integrated rate laws. For what? The 0th, the first, and the second order. For which order is this one? First, right? So make sure you pick the right equation to get the job done, right? Don't grab a hammer if you need a screwdriver, that's all I'm saying.
The first order one is what? Natural log of a to the 0 equals.
Okay? So we know we have to use this equation. How many variables are in this equation? Well, we've got the natural log after a given time, we've got K, we've got T, and the initial concentration, right? What information are we given?
Initial concentration.
Right? So we have the initial concentration, so we can plug that in there, right? What else? We're given time, right? So we have that value right there. Right? And what is the question asking us to figure out? Where's another go? Right? We need to figure out that right there. Right? So we're giving the red, we're giving the purple. What do we need? We need what? K, right? Well, we're given some other information, aren't we? We know that this is a first order reaction and we're given a half-life. Do we have a way of relating K to our half-life? Yes. So what's the first thing you guys need to do? After you pray and cry, after that.
The half-life is equal to 0.693 over K.
Right? There's our way of relating K to our half-life. Can you guys figure out the natural log of 2? Thank you. Right? And we have the value of T1 half, right? So can we get K? Sure. We can just plug those together. And, right, so natural log of 2 divided by 400 equals, let's see, 1.73, and I ran out of space, so I'll write it over here. 1.733 times 10 to the minus 3 per seconds, right? Per second. Does that make sense? Right? This is a constant, right? What's happening per second, right?
Isn't K supposed to have some other stuff, like?
It can, right?
Okay, but it
But,
doesn't have to.
but this is what we have here, right?
Okay.
Yep.
for the red one, why are we putting in the half-life instead of the time it's asking for?
Oh, I'm sorry, you're absolutely correct, I underlined the wrong one here. Thank you for pointing that out, thank you. Whoops. Sorry about that, good call. Cool. Now can you guys plug in the rest of it? We got K, we got the correct T now, and we've got our initial concentration. Yep.
I have a question about one of the integrated laws.
Mhm.
So like the concentration, the initial, and then does this just mean at a certain time?
At this time here, yep.
That time there.
Mhm.
So if I'm putting that in this here, so it's 200 seconds.
Mm-hmm.
How do I push that in? Well, I guess we're solving for that. So
Mhm.
1600. we found
Here's,
that.
it's first order. Right?
Oh, yeah,
Yep.
1600.
Found that, and you have that.
Now,
Mhm.
okay, I just needed to work that through, so I wanted to, I guess, specify.
Mhm.
Okay, thank you.
Yep. Okay. The units in 1/2 Yeah, that's what they. Yeah, because remember, natural log of 2 is unit was, I think it's 400 seconds, right, so K is. And you'll see how that's important when when you set up the whole equation. That's our initial. Right? So take a look at the way I call it, like the purple goes into the purple. No, that's what you're trying to figure out, right? So that's the green part is what you're trying to figure out. Look, no, you have K, the K's the 1.7.
Wait, what?
It's an actual 1 2.
Just kidding.
Yeah, that's it.
That cancels it out. You would like, yeah, like when you do, like, you would put it to the power. Like,
So it's
you
like
would do
after
the
16
natural log.
has 1, says 11.
Yeah. And then it would cancel natural log and E, just be one.
Mm-hmm.
But this would be a variable.
That's,
So then-
yeah, that's.
So it equals that.
Otherwise you think that, I have to give you information, calculate the K is, otherwise you have to.
Well, we have to put the other side to E too, so that, cause you have to do it to both sides.
Oh. I don't know if you can really use these, so it could be wrong,
So
but,
where's that? So that.
because you've got a constant.
So that's why they put it there on the calculator, because those are the opposite functions.
I don't know if you could use E here, because you've got a
So the
constant
E
plus a
to
log
this
on
will
one
get you
side.
this concentration.
You don't have a
and
constant.
Right, it's equal, and then E to the other side.
Yeah, but
Right. Just like if you multiply by 2, you have to multiply
the
both
natural log
sides.
of
Right?
0.5.
Yeah, I just
Oh,
combined.
wait, why
is it like this?
So I have
I
the
don't know.
natural log of
That's what I
the
think.
concentration.
Oh, it
and the
is.
time we're
Looks,
looking at
yeah, looks good so far.
equals.
Okay, well, I love that.
Cool.
And when you put it in, they will
Yep.
turn on.
Well, you need to get rid of it.
Yeah, but it's completely different number. Like, no, it's the.
How do you, I still don't. I just took the natural log of that in the calculator. Oh.
So if I answer your, right, if you multiply this side, you multiply this side. If you multiply this side, now you get to do this. That's what.
We just divide it by natural log. Does that work? I don't know. Because it's really good. It's
Not
not
the
if you don't
natural
solve
log.
this one out. Yeah. I don't think. But you have to put a natural log of something.
Yeah.
Just be a natural log.
That's the way math works. I really don't, it's a good question, I wish I had a better answer, but. That's all I can
Okay,
say
now I
at the
got
moment.
that.
That's-
So what's the units?
It's multiple.
Okay, well, what's that matter?
Yeah.
So now we just need to start something, right?
How do you do natural log?
So get rid of natural log, you have to go E to the,
That's what, okay,
so you should get,
So that's
should get a
from
answer
the
on right side.
rate, that's from the half.
See if we have similar equations.
Andy?
So.
That's what he's
Yeah,
saying.
for trying to get the
What did you
constant,
get?
I got rid of 1.6.
Oh, you got 1.6.
Right, because you think of half-life defined by when
So
it
you
gets to
did-
the constant.
so you did
when it gets to
negative
half-life.
I got neither of those.
You did
So if
negative
you take a look through my slides,
1.733
it'll show you exactly
times
how
the
that
negative
falls
fifth,
out.
right?
Right, but that's always what it's gonna be
It's
for
10 to the
a
negative
half-life.
third.
Not for every
Third,
reaction.
oh, okay.
That's for half-life, okay?
Oh.
And then you multiply that by 1600,
Right.
and then you plus 0.5.
I think you have to do natural log of 0.5.
Oh, is it?
Yes,
Okay.
Yeah.
don't forget the natural log.
And then
So
that.
you have to like take
and
each
then
of
that's
that.
into the- that.
Yeah. Wait, so then why did I get different?
He just skipped right over us.
we're confused. No, you got the same answer. I just moved this one.
Oh,
Let's see here, natural log. Oops. As we start to plug things in, natural log of A t equals negative times our K value, 1.733 times 10 to the negative 3 per second, times 1600 seconds, plus the natural log of 0.5. Right, good? So we should be able to simplify this side down into one numerical value there.
wait, we're not using the units for A of 0?
I mean, you can put minutes concentration, that's what the brackets mean there, right?
But wouldn't the units keep that all from adding together?
No. This is per seconds, right? This is seconds, so this ends up as a unitless value, right?
Right, but the I'm saying the value of A at 0,
Mm-hmm.
wouldn't we write it as?
What are the units here? They're gonna be the same as the units for whatever this is, right? So,
Okay, sorry.
no, it's okay, it's a good question. I didn't write that down for some reason, so can somebody tell me what all that adds up to be?
Negative 3.46.
Negative 3.46? Okay,
Um,
I'll take your word for it.
Maybe?
Okay, no, that's fine, I believe you guys. Right, how do we get rid of a natural, right? We don't need that, we need this. How do we get rid of a natural log? E, right? So we do E to this and E to that, right? And so then this side simplifies down to the concentration of A at time t, and over here I got 0.0312, right? And this is moles, right, per liter, our concentration. Good? Is this tricky?
yes.
Yes. Is it gonna get easier by you saying, well, this is tricky, I'm gonna leave it for later? Is it gonna get easier if you have that approach to this? We hope, right? Now, let me ask you an honest question, you don't have to answer, although if you wanna inflate my ego this morning, that's fine too, okay? Did I make it seem easy when we went through it? Why is that? You think when I was sitting in your seat many years ago now, right? Over 50 years ago when I was an undergraduate. I'm just kidding. Right? Do you think I looked at this and said, I got it, 100%, this is easy, right? No. So what's the difference? What's the only difference between you guys and me? And now I'm being very honest. I promise that you guys out there are smarter than I am at math. I'll just go ahead and say that, right? So why is this easy for me? What's the only difference then?
Practice.
You gotta do it. You gotta work some of these problems. That is the big secret to Gen Chem 2, okay? You gotta work some practice problems. When? Well, we got an exam tomorrow morning, and it's, I'll start later on tonight, right? We'll work a couple practice problems later on tonight. It's not gonna work, okay? If you guys do 15 to 20 to 30 minutes each day, just picking 2 or 3 problems to start to work through them, okay? Just each day, just start doing it, okay? And this stuff's gonna get a little bit simpler, I promise. All of the problems are worked the same way. I only have so many equations I can give you guys. There's many different ways to ask it, right? But they're all solved essentially the same way. So just work a couple problems, right? How much did you guys spend on the book? Some of you guys way too much, right? I'm sorry, I didn't pick the book. Right? But you paid for it, so why not use it, right? Just like you paid for my time, right? That's why I have office hours, right? So come by and ask me questions if you have. Or not, I know, I get it, I'm scary. I don't like talking to people with red shirts, I'm not gonna go to his office, okay, fine. Right? But then go talk to Laura, or watch a video online, oh, she's not here, but I was just kind of pointing at an empty seat, right? Right, or whatever it might be, right? Go talk to your friend who already got an A in this class. Do you guys know somebody like that? I know, Dr. H, all my friends are dum-dums, they failed it, right? Huh?
Does Brianna?
Yeah, she passed this class. Like, I don't think I had her for Gen Chem 2 though, so I don't know. Not that I could tell you were great anyway, right? You had a question though?
With the practice problems, do you suggest like one sentence or chapter?
Absolutely. I am not an overly creative guy when it comes to writing exams. I take a look at the back of the book and say, I assume my students have worked through these. They will appreciate seeing the same problem that they already know the answer to. And then I put that into the exam. And then what happens is, Dr. H is very unfair on his exams. He gives us problems that are nothing like what it's in the book. Like a read these end of semester and you review them like, but, and all joking aside, that's what I do. Now, I might change some of the numbers, right? I might ask it just a little bit different here, but I'm not gonna go, there's only so many ways I could ask this question, what I'm going to get to, right? That's all it really comes down to, okay? But yeah, definitely look through the stuff in the book, okay? Cool. Yeah, that's, you know what? We will, that seems like a good time. We'll let this soak and settle, and we will pick this up on Friday. Yeah.
Those problems are impossible. They're impossible.
Think about how many problems are on online. Have you ever looked at practice problems online?
Yeah.
They have answers, there's